Thanks. Well, again, also thank you very much for inviting me, both from the Crafoord Foundation and from the Academy of Sciences, and thank you to all of you for coming. I think it's always extremely inspiring to see real people coming to attend a science lecture. Oftentimes, you see a lot of yourself sitting out there, and now suddenly you see a lot of yourself as you remember yourself 50 years ago. So that's very nice. So I've given the title to my talk, Geology, Our Key to a Wonderful Future on Earth. And that is partly because it seems like for a long period of time, both in the sciences and in the world of culture, we are focusing on problems. We are focusing on something that even a new concept come up called polycrisis. I mean, it's the worst word I ever heard. Because it's also, of course, again, the world is a very generous place, and when you study it in a geologic with a geologist's eyes, you can see that it has an enormous expanse of time. And during that enormous expanse of time, all kinds of things have happened. All kinds of conditions have changed around the world, about the Earth, but it still remained its functionality and supported life. And I think that we should also remember that our aim and our hope is not to survive, it is to live. To live is much more important than to survive. So I think you should forget about all the, I'm sure we all have anxieties and worries, but try to forget them as best you can. Not to be reckless, but to see opportunity and try to pursue it. So I think we have a wonderful future on Earth, and how do we get that? How do we achieve that? That we do by understanding how the world works, how the Earth functions, and then we can make it work to our advantage. So let's just present the topic of our lecture today. This, I guess you can all see what it is. This is the planet Earth. And you can see that it's a very, very complex system with many, many parts. It's also, as far as we know, a unique system. We know nowhere else in the universe where something like that has to be seen. And we can see that it has component parts. It has continents, these are these things. It has oceans, it has clouds, it has an atmosphere, a very thin atmosphere, we can just see it here. And it has a size that is kind of finite, so it's kind of also a closed system where everything that's in there has been there through the whole Earth's history, more or less. So geology is understanding how did that come about, how did it become stable, and what is the history of it. And I think it's quite important that we understand that none of this is a given. You might think that a planet is just like like a planet should be. We have an Earth; it will look like that. But this is a result of billions of years of interaction between the life that lives on this planet and the planet itself. And you can also see that it has these component parts here, but if you look at other planets in our solar system that are exactly like Earth, like Venus is almost the same as Earth within 1% or so, it's completely different. It's 500 degrees centigrade on the surface. It has no oceans, there's no continents, it has no nothing. It's just a big, very barren and very hot place. So it's not a given, but there's something that makes this work. And I'll try to introduce us to what is it that makes this beautiful place work and be stable over time. But talk about science. What is science? You would also, of course, in every period of of human history on Earth, we have been performing science, and we have been recording science, and we have been communicating science. Here's a maybe 25,000-year-old painting from a cave in southern France, and you can see it's a natural history book, basically painted on the wall. It is all the animals that you were dependent on. It shows the concept of an ecosystem where everybody have their own role. And basically it has been a way of doing two things, I think. One is to inspire awe with the beauty of the world we live in, this fantastic art. But it also tells us that we need to understand the world we are living in to be able to live within it. So science has been here forever. And you will find at times various cultural trends trying to say that science is, obsolete. Science, we shouldn't do science. We shouldn't do all of this kind of stuff. Get rid of all these professors. But of course, you can see it's an intrinsic part of being human is to perform science. So those who want to get rid of it, good luck. I think we will prevail. Also, science have served real concrete you could say, purposes for humankind. Here's the Stonehenge in southern England, and that is an astronomical installation. So very early on, we understood that in able to be able to do agriculture, which was a development that happened 10,000 years ago on Earth, we need to be able to predict the seasons. We need to have an idea of predictability. So I think that's another thing that's really important relative to the role of science, is that we use science to be able to predict what is going to happen if we do something. If we have a system we live in, if we perturb it in some way, we need to know what happens to the system. Or if the system perturbs itself, we need to know how to respond to that. So science is also to put predictability into our lives. And this is, again, to predict when should you sow, when should you harvest, and so forth, based on the astronomical position of Earth in its annual cycle. We are now in southern Sweden, and we were at some point in southern Denmark. And now we have better sound. And I think it's quite important when you talk about research to, of course, to remember that this is the locus where science as a definitive trait was introduced. Tycho Brahe, who lived out on Hven, was the person who came up with the fundamentals of modern science, that is, that you have to base your conclusions on observation. So before that, science and philosophy were closely related. They should be, they still are to some extent. But there was a time where you think you could rationalize into conclusions about how something works just from philosophical background. But Tycho Brahe came to the conclusion that you need to observe the stars to understand how the solar system and everything else works. And basically that was the foundation of modern science. About the same time, there was another person, and since today we are celebrating the geosciences, I'd like to introduce you to this person here called Nicolaus Stenonis, or Niels Steensen. He was a Danish, he was actually a polyhister. He was engaged in all kinds of sciences. He did medical anatomy to a fantastic extent. He also introduced a new science of geology, and he did many, many other fantastic things. Back in 1668, he published a paper that was quite revolutionary, and it gives hope to all of us because it's a very, very famous scientific discovery he did. And it happened to be that he realized that if you pile stuff on top of each other, what's at the bottom is what you put there first. And that was a groundbreaking scientific discovery. Everybody in the whole world were completely amazed by the wisdom of this fantastic scientist. So Steno, he put something into the sciences, and that was time. He said that if you go out and look in nature, you see that there are layers that are out in the mountains, out in the fields, whatever. If you use the principle that what's at the bottom came before what's at the top, it means that everything you look at out in nature is a time sequence, represent a time sequence. So before that, it was assumed that the world was done as a package deal. The whole Earth was created by God, and then it remained like that, and we just lived on it. But Steno, he said, well, actually, the Earth and the world is a result of a sequence of events that are all stacked on top of one another. So he introduced what is now called the geologic timescale, that basically we have that the geology on Earth represent a record of everything that's happened through Earth's history. So thank you, Steno, for that. So what can we do now to get an insight into what happened on this planet? How does this world function? And since I'm from Greenland, and since Greenland is the most wonderful place on Earth, of course we will go to Greenland to start our journey into the evolution of Earth and all the component parts that we like so much about it. So welcome to Greenland. Here we are flying. That's another good thing about being a geologist. You get to fly helicopters and sail boats and go dog sledding and all these wonderful things. So you have to get used to that. Anyway, we are here in Greenland. You can see the Greenland ice sheet in front of us, and you can see these mountains in the back. And they have just been, the ice has just retreated from these mountains, so they're completely fresh rocks that are just polished by the ice and sitting there ready to be studied. We go to this area to see what we can find in the ground. And this is an area near Nuuk and the west coast of Greenland where we found out about maybe now many years ago in the 70s, 80s, found out that these rocks that we see here in the background are extremely old. They are the oldest part of the geologic record on Earth. So let's just find out how old they are, these rocks. Well, you see here a chart that shows all time in the universe. All time that have existed in the universe is showed in this graph. And the rocks you saw in the background in that figure were formed here. So they have experienced more than a quarter of all time that existed in the universe, and they still have a memory of what have happened in that quarter of all time that have existed in the universe. I know there's also a Crafoord Prize for astronomy, and of course this is the work of astronomers, and they are all very impressed when they say, we can see this galaxy that is X light years back in time, and da-da-da-da-da-da. Of course, as geologists say, I can pick up this rock that have experienced 1/4 of all time in the universe and can tell me a story about it. So this is where we are in time when we go and look at these rocks. So then we'll probably think that these rocks are very odd and very strange looking and exotic because they are from the absolute dawn of time, the first beginning of time on Earth. Let's look what we find. Well, step out on the helicopter, go and look at the rocks, and we see something. It looks strangely familiar if you are geologists. I can see maybe most of you don't find this very exciting, but this rock is extremely exciting. When we started looking at these rocks many years ago, it was a dogma. It was known from physicists, no bad words about physicists. They can get the Nobel Prize if they need something, but physics, of course, would tell people at that time that oceans didn't occur on Earth until maybe midways into Earth's history, after a few billion years, because we see water vapor come out of volcanoes, so water would have accumulated over time slowly and started filling up the oceans. What they didn't understand is that water coming out of the volcano actually ran in at the root of the volcano from the ocean that's already there. So anyway, there was supposed to be no oceans on Earth 3.8 billion years ago when these rocks formed. And yet we see this wonderful rock here. And why is this wonderful? Well, it's because you can see these sausage-shaped objects here. These, we know what they are because we can observe them being formed on Earth today. And what they are is they are caused when a volcano has an eruption underwater. So the hot magma comes out, hit the cold water, forms a glass rind, that's a black thing we see here, and it keeps the molten lava inside so it doesn't get in contact with the cold water and it cools more slowly inside. Sometimes it breaks through and another one comes out, and this is how it builds up like this. So without any strange instruments, anything other than our eyes, we can go out, right out of the helicopter, say there was an ocean on Earth 3.8 billion years ago, because we can see this. It also tells us another thing that's very interesting, which we didn't know actually, and that is that Earth is an incredibly boring place. You can imagine that this one was formed 3.8 billion years ago. This formed 2 minutes later. Maybe it took 30 seconds to form it, and it's still sitting there. And they've been sitting next to one another for 3.8 billion years. 3,800 million years they've been sitting there, and nothing has happened. So Earth is not a dynamic place, as we oftentimes say it is. It is actually a desperately kind of boring place, I would say. Okay, so now we learned that. That's interesting. What else can we say about Earth when we walk around? We walk a little bit around. Oh, this is just to show you what it looks like today, the principle that we can use observation from today to understand the past. You can see these sausage-shaped objects here from a lava field in Hawaii. Anyway, if we walk further around in this old complex of rocks, we find other rocks that, again, without any analysis, can tell us something about the early Earth. This is called banded iron formation. It's an iron ore that you have in very old rocks. And we can tell that it is formed by precipitation of these minerals out of the ocean and deposition on the ocean floor, again 3.8 billion years ago. But when we look at the minerals, it's an iron oxide mineral and quartz. So the black stuff, these black layers are iron oxide, and the other stuff here, the white, is quartz. And that's all they consist of. Well, when we look at that, we can immediately tell two things that are really important about Earth at that time. One is there was no oxygen in the atmosphere, because we can see that iron was dissolved into the ocean and then precipitated out. Iron is not soluble when it's oxidized. You all know rust on your bicycle, whatever. That stuff you cannot wash it off with water. It doesn't work like that. So you have iron that was dissolved and for some reason precipitated. So if iron could dissolve in the whole ocean, there could have been no oxygen in the atmosphere. So our atmosphere has changed composition over time. That is quite clear. The other thing we can say, which is maybe less obvious, but that is that if there had been a lot of carbon dioxide in the atmosphere, if there had been a lot of greenhouse gases in the early atmosphere, which some people have speculated for many good reasons, iron would not be soluble either, because it would form iron carbonate instead, another insoluble component. So we can just, again, without any instruments, but just looking at the rock, we can say something about the atmosphere on the early Earth. Actually, we can also say from the lavas we saw before that something about the atmospheric pressure, and it was something like today. We can say that the carbon dioxide content of the atmosphere was somewhere in the same range as today. So again, enormous stability over almost 4 billion years of these characters. Well, what else can we say? At the time when I started working on these rocks, there was one thing that was absolutely certain, and that is that life could not have existed on Earth earlier than 3.5 billion years ago. And we knew that because the Apollo mission had been to the moon and had brought back rocks from the moon that we could analyze. And these moon boots, when they come back into like this to get all the dust off, the lunar dust off, if you look at that dust, there are tiny little spheres of glass. Because every time a meteorite has impacted the surface of the moon, it evaporates the stuff, it condenses into little dewdrops of glass that fall down. You can measure the age of each individual of these little dewdrops by isotopes. You can ask Wolf about how to do that. And when you do that, you find out that the enormous craters that are 1,000-kilometer sized craters on the moon that we call the lunar basins, the mare on the moon, we can find out that they would have be caused by impacts that happened about 3.5 to 3.7 billion years ago. So what it showed us, these rocks from the moon, was that the moon had been impacted by enormous meteorites up till about 3.5 billion years ago. And every time such a meteorite would hit the moon, the temperature on the lunar surface would be above 4,000 degrees, just from the impact energy. So of course life could not live on such a planet, and there would be no water either on such a planet. So we knew that. Anyway, we go to Greenland, and the next rock we stop by looks like this. That's interesting, of course. I can see you are all excited again. This is really interesting, because this is not a magma rock like you would have you have magmatic rocks on Venus, on Mars, on the moon, everywhere, even on asteroids we have them. But here we have something that is caused by deposition of sediments, of particles in the ocean. So we have a gray layer here and some black layers here. So that's really, really, really interesting, because it tells us something about what else was going on on the planet at that time. And if we look, we can understand how this formed. This is formed by a mud flow, by an avalanche of mud that come tumbling down some slopes and landed on the ocean floor. That would have taken maybe 5 minutes to deposit that. So again, this testimony to the boringness of Earth. This thing happened 5 minutes of activity, 4 billion years of nothing going on. Pretty desperate situation. This stuff here, on the other hand, is a slow accumulation of tiny clay particles. And clay they deposit on the ocean floor at a rate of about 1 millimeter per 1,000 years. So this is a complete different thing. This every day on Earth is recorded here. What was the normal background situation in the ocean, which is the largest part of the Earth system? So let's look a little bit closer at these things and see what we can see. So these black layers look like this when you look at them in the microscope. There's only maybe a few millimeters across here. You see extremely finely laminated, extremely fine sediments. Some layers are completely clear and some layers are completely dark gray. So let's look what they consist of. Again, no instrument other than the microscope and your eyes. You look at this, and you can see that this is quartz. This is muscovite, a mica mineral, so colorless minerals. So the reason why this part of the rock is black is because you have tiny little particles of something black. And just again with your eyes and the microscope, you can see this material is carbon. It's graphite, like in a pencil. So how could that be? Well, that's a big mystery, actually. That's a very big mystery, because we know there was no life on Earth at that time. But we also know that on Earth, the most common element on Earth, would anyone have an idea what could be the most common element on Earth? It's oxygen, not the gas, but the element oxygen. Every other thing on Earth is combined with oxygen to oxides. All rocks consist of oxides. And carbon also is oxidized on Earth. All carbon is oxidized. It's carbon dioxide in the atmosphere, it is carbonic acid in the ocean, and it is limestone in the mountains. So carbon does not exist as the black stuff we call carbon on Earth in its normal form. So on Earth, the way that we form carbon is basically by biologic activity. Organisms take carbon dioxide out of the atmosphere, and they make organic matter, and the basic organic matter we all know is called carbohydrate. So carbohydrate is basically just a combination of carbon and water, which is quite unstable stuff. So over time, the water breaks off the carbohydrate and leaves the carbon behind. So that's how you form carbon on Earth. Start with organic matter, but how could you start with organic matter if there's no life on Earth? That's not so easy to understand. Anyway, you know, experimental science, geology is an observational science, not experimental, but we can actually do an experiment, and I will encourage you all to do that. Talk to your mom and dad before, or maybe after, better you do it. So you can do an experiment. What happens to carbohydrate if you heat it? So this is what happens to carbohydrate if you heat it. You take a chicken, put it into the oven, up to 200, give it 250 if you have a good oven, and then sit for a couple of hours and see. And what happens is that you have basically turned the carbohydrate, the organic matter, into black carbon. If you take these rocks here and Isua, they have been put in the oven for about maybe 20 to 50 million years at 550 degrees. So if you have an oven like that, of course a similar situation will happen. But what's really important to this experiment is if you let it go even for 20 million years at 550, the carbon will still sit there in that tray. It will not go away, it will just be preserved. So this will leave a lasting trace of something that was at one time on Earth. So this could indicate that actually we did have life on Earth 3.7, 3.8 billion years ago when these sediments were formed. But how could that be? And why is that potentially important for us to understand that? But of course, just because we don't have any better idea than it was organic matter, it doesn't mean that it would have been life that made this black stuff. So we are so lucky that actually living organisms, they make carbohydrate from two different isotopes of carbon, carbon-12 and carbon-13. They are two slightly different versions of carbon, but the process of making it with carbon-13 is a little bit slower than it is for making it with carbon-12. That means that organic matter has a deficit of carbon-13 relative to the normal carbon in the atmosphere around you. So by analyzing the carbon that is left, you can see if it has been through a living process first or whether it came directly out of the atmosphere by some other process. So if we analyze this rock and the carbon we find in it, we find something quite interesting. It has a deficit in carbon-13 of 26 per mil, minus 26 per mil in that, which is exactly the same as if you take broccoli or something from the fridge and put it into the oven, or chicken, whatever. So organic matter today has exactly the same isotopic composition as this carbon we had 3.8 billion years ago. That again goes back to the boringness of Earth, that this mechanism to make organic matter was invented once 3.8 billion years, or maybe earlier than that, and has not been refined since. Every organism still does the same thing. Today the enzyme that catalyzes that process is still the most common protein on Earth. So very little happened here. and we are very slaves of our habits, it seems. Also, you might think when you look at this diagram here that AI has not really entered my world yet. I could have probably made some nicer diagrams. But the reason why it is kind of a bit clumsy is that it's written with one of these rocks. So it tells us something else. There's enough carbon in these rocks that you can write with it, which means that the life that lived in that ocean at that time was not sparse. It was not a rare thing. It was not primitive life. It was primitive in a sense, but it was not kind of the beginning of life on Earth, because it could sustain a steady flow of organic matter to the sediment. So just by getting that number and the fact that we can write with it, we can say that for sure at that point in time, we can do many other things, but the fundamental idea comes from there must have been some source of energy that could sustain this life. And that source doesn't exist in the Earth system other than one thing, that's the sun. Solar energy is the most intense energy on the planet. So if they could sustain themselves to do this fantastic job, they must have been able to do photosynthesis 3.7 billion years ago, 3.8 billion years ago maybe. So that means that basically all the fundamental parts of Earth's system were in place that early in Earth's history. And that's really important because it allowed the Earth to function in a way. And here it's important to understand why photosynthesis is so important and why life is so important. So the energy to perform processes, all processes happen because you want to convert energy from one form to another. So all the energy that comes out of the Earth itself as a planet, the enormous planet, that is very, very little. If you take a square meter here, you go 6,350 kilometers into the core of Earth. You have a wedge like that, a layer cake piece like that. Within that whole volume, how much energy is converted? 0.1 watt. 0.1 watt, that is nothing. So you are a 100-watt engine. Your brain is burning 20 watts now. This Earth has 0.1 for the whole goddamn Earth underneath here. So it's a very, very slow system. It doesn't work. But up here comes the sun with 340 watts per square meter coming down here. So if you can tap into that energy, you can do everything you want. So that's why life that first happened on Earth decided I better tap into the 340 watts than to the 0.1 watts coming from below. And that's why photosynthesis came. And photosynthesis completely changed the way the Earth works. So basically, when photosynthesis came into function, this looked like this. You have organisms that take water and CO2, combine them to make organic matter, and leave oxygen as a waste product. That changed the world completely. And basically, the energy that is brought into sustaining the Earth system by organisms being able to tap into the solar power is maybe 3 or 4 times more than all the energy that the Earth has for its own internal machinery. Okay, so how does that then work for us? Well, now we have this process has been going on for 3.8 million years. We do this, we take water, CO2, make it into organic matter and oxygen, and that is how all energy, all processes on Earth happened. And now we'll take a big jump, 3.8 billion years into our own time, maybe 10,000, maybe 100,000, maybe 200,000 years ago, when humans came on Earth. And what did that do to the Earth system? Well, it did something very significant, and it's really important that we understand who we are and what we did. Because this thing happened. Humans decided that it was a good idea to outsource energy conversion. Before that, the only way you could return or reverse that process from photosynthesis is to eat something, take it inside yourself, and then burn it inside and make the energy, and you could do something. But what if you can outsource that burning of the energy? You just make a fire, and you can heat yourself rather than having to eat stuff to heat yourself. You can also do many other fantastic things. And in the middle of the 1700s, there was suddenly a fantastic breakthrough in science, and that was that people realized that energy is the same regardless of which form it takes. And basically, they realized that you can convert heat into work. And that when that happened in 17-something, steam engine, whatever, everything became mechanized. Today, every human on Earth have about 30 human powers of energy available because we learned how to outsource. This is the first time it happened in all life on Earth, is that we could do energy conversion outside of our bodies, and that gave us what a fantastic, all the wonderful things we cherish in our world is derived from us being able to convert energy from outside ourselves. But of course, it turned out at some point that there were some consequences of this. And we didn't really realize that until quite recently, that when we burn material, fossil fuel, tree, wood, whatever, we produce more carbon dioxide that we did let out to the atmosphere. This is a piece of an ice core from Greenland where you can see little bubbles of ancient atmosphere, and you can see the ice, and you can, with isotopes, you can tell the temperature on Earth and the content of CO2 and whatever at that point. It's a long story, and it's not the story of today, but it has a fun and interesting, you could say, relevance exactly where we are now here in Sweden, and also in Denmark, and also in this intersection between science and also medical sciences and so forth. Because this is a paper that was written in 1904 by a Danish physiologist who went to Greenland to study the physiology of Inuit people when and how they metabolize stuff. But when he did that, he had to be able to measure carbon dioxide concentrations very exactly. He was called August Krogh, and he was the founder of Novo Foundation, which is now the big Novo Foundation, Novo Nordic, insulin and diabetes, whatever. So there's many parallels to the Crafoord story. Anyway, he went up to Greenland to study this, and he had to do all kind of interesting stuff. But what he needed to do was to measure carbon dioxide concentration very accurately. And while he had found out, he also went out and measured the carbon dioxide in the air and in the water, whatever, in Greenland. And he realized that the concentration of carbon dioxide in the atmosphere in Greenland was higher than the equilibrium concentration in the water that was in the fjord below. So he said, there must be leakage of CO2 into the atmosphere, into the world atmosphere. It must be growing, the carbon dioxide. He said that in 1904. And then he referenced Arrhenius, Svante Arrhenius, who is a very famous Swedish scientist. And in 1896, Arrhenius, he made the hypothesis that the temperature on Earth's surface scales to the carbon dioxide concentration of the atmosphere, and he called it the greenhouse effect. So this all was figured out in the beginning of 1900, and August Krogh proposed at that point that you should make an international organization to monitor this, because it would change the temperature of Earth over time, the industrialization of the world. That didn't happen, so here we are. But then, don't despair, because of course geology can help us get back on track. So I told you that when we look at these 3.8 billion years old rocks, we can see that the carbon dioxide in the atmosphere was kind of the same as it is now. And if you look through the whole Earth's history, it turns out that it has been balanced at somewhere of the same level. And there's no reason why it should be like that, unless it was that Earth has some kind of regulatory mechanism that can do that for us. And it turned out, as late as in the 1950s, people started to realize that we have a balance of carbon dioxide coming out of volcanoes being absorbed again back into Earth, and the absorption mechanism or reaction mechanism is called weathering. That is, the rocks, they basically react with carbonic acid, that is CO2 dissolved in water, and they bring the carbon back into the ocean and back into Earth's mantle. So these two processes have been in balance for maybe 4 billion years. Also, we can see that there's a thermostat in that. That is, the reaction goes faster if it's warm, it goes slower if it's cold. So it's a little bit colder on Earth. The CO2 builds up, you get more greenhouse effect, and the world gets warmer. If it's too hot, the reaction goes faster, take out CO2 faster, and we go down. So we have a thermostat that has protected the whole world for 4 billion years. So when humans suddenly came in with a third source of CO2, namely the burning of fossil carbon for the first time, then suddenly the natural reaction to bring CO2 out of the atmosphere could not keep track with the incoming CO2. So what can we do? Well, we can understand what the weathering process is. And the weathering process is that rocks, again, react with the atmosphere. They can only do that at the surface area. So it will scale to the temperature, we know that from the thermostat, but also to the surface area of rock that is available for this reaction to happen. And most places in the world, the rocks are just, as they are. But in Greenland, we have a fantastic engine going. That is the ice cap, the Greenland ice sheet you see in the background, 3,000 meters thick layer of ice that is moving across the mountains and grinding all the rocks into a very, very fine powder. Flushing out the powder with the meltwater and dump it in the fjord somewhere nearby. See, that is very interesting because this very fine material, of course, would have enormous surface area, and it's caused by the glaciers. But on the other hand, it's in the Arctic, so it's at 0 degrees, and the temperature is very low, so it doesn't do very much. But does it do anything anyway? Well, we can look around Greenland. This is a map of chlorophyll in the ocean, and you can see up here is Greenland, Iceland, Norway. Everybody on Earth have been, for the past thousands of years, been going up here to hunt whales and fish cod and whatever, because there's enormous productivity in the ocean up in this area. And why is there enormous productivity in the ocean? That is because the productivity in the ocean is dependent on the access to minerals from the continents. So the ice sheet is pumping out minerals, and they sustain a lot of life in the ocean here. See, in the tropics, you would think there'd be a lot of life in these parts of the ocean. They are marine deserts. Nothing happens in the tropical oceans because there's no nutrients for the life to sustain itself. Okay, so that's interesting. Also, if you look at the glacial front, you see the ice in the background. You see on land the plants in Greenland. You can see why Greenland is called Greenland. It's hysterically green in the summer because the plants are getting all the nutrients they could possibly ever wish for. So they grow like crazy. Now let's take a global look. What is the situation of the Earth as such and humanity? Well, we can look at, for instance, a satellite image. You can see Greenland is up here. There's not very much life. You have Iceland over here, a little bit Reykjavik and whatever. But then you have all these enormous concentrations of light in a girdle around the northern hemisphere here. That is where all the wealth is on Earth. You can measure the wealth of a country with a photometer from a satellite. Better than the national bank of that country can give you the number. Because people are so strange that every time they get more money, they put a switch on more light. We don't know why we do that, but that's what we do. Does that have anything to do with geology, you would say? We, of course, as citizens in this very rich part of the world, would say it's because we are smarter than everybody else. But if you look at it, of course it has geology. Everything on Earth is geology. So why is this geology? Well, that is because the Ice Age 10,000 years ago went into, this is just the last push of the last ice age, but basically this orange belt that's running across here, that is the margin of the ice during the last ice age. This is the margin of the Himalayan ice sheet, and the color here is what's called crop intensity. That shows how much yield does a field provide per hectare. So it basically says, where is agriculture very economical? Where does it provide a lot of product for you? That is in this very rich belt across the northern hemisphere. Look at Africa. There's there's no orange and hardly any yellow. Very few spots here and there. In Australia, south coast, we have some. But by and large, all the food we eat on Earth is produced in very few countries in this part of the world. So, what does that mean? Well, it probably indicate again that these glaciers were the source of the minerals, of the nutrients that make everything grow here. So what is the process by which these minerals then release the nutrients? Well, that's weathering. The only way that the nutrients are released is with the weathering of the minerals. So we have two things going on here. We have here in this area, we have a large uptake of carbon dioxide, and we have a large release of nutrients to plants to grow. So go back to Greenland. I was in Greenland, and my daughter had the brilliant idea that she would make gin and tonic. And she decided to go out on the fjord as an iceberg, take some ice for the gin and tonic. And it turned out that it was a really bad idea, because there's this mud, which is this ground up rocks from the ice that was sitting here on the shore. Her rubber boot got stuck. One of them we got out. We got my daughter out, luckily, but the other one's still there. So four people could not pull it out. And if you had, in physics, you have something called van der Waals forces. That is, if there's a very close connection between things, they get really, really sticky. You know, a gecko can walk on a ceiling, for instance, with a very sticky feet. Well, What this shows that you can't pull a boot out again, shows that this material is not fine-grained, it's ultra-fine-grained. There's enormous surface area on this rock flower. Okay, so maybe we can use this information for something. Well, we can also look, it's coming out with the meltwater rivers. It gets deposited and dries up to this fine material. It has, over the past 10,000 years or so, it has formed enormous deposits all over the place. So maybe we should look a little bit more into that. Is there some way we could activate this for our purpose? You know, how can we get this to work for us in a way so we can get higher crop yield for a growing world population, and we can lower the CO2 content of the atmosphere and mitigate the climate changes. And why is this? Why would this be possible? Well, as you can see, this is in Greenland. You can still see there's snow and ice sitting covering this. It doesn't react in Greenland at all. But what if we took it to warmer climates, places where the ice has not been during the last ice age, where the potential is there, but we just need one component to set it off? That is the ground-up rocks. So research is necessary. This is not what we do. These are what the people who do all kind of strange molecular biology or whatever. No, we do the real kind of research, like this. We go to Greenland, scoop up some of this stuff, do like this. That's great fun. So we are here homogenizing a ton of this material into something we can use for doing trials and tests and see if it can actually do some of these things we are thinking about. We also look at the material properties. Here is a little pile of this material from the ice, which we call glacial rock flour. Here's a cubic centimeter of granite. Granite is what is the rocks under the ice, and that's kind of what's ground up here. But you can see the surface area that can react with the environment here is 3 square centimeters about, whereas when it's been under the ice, it's come out to 200,000 square centimeters. So 70,000 times more efficient. We'll basically say that from going from geologic timescales, it goes into human timescales. So can we do this? Well, let us try. So we took some of this material and sent it to Ghana in a collaboration with the University of Ghana, put it on these poor depleted soils they have in Africa, sowed some maize, and let it go for a while and see what happened. And here you can see the field trial after a season. This is what a cornfield, a maize field in Ghana would normally look like. You can imagine how desperate it is to be a farmer in a place like that. You do everything right, and still this is what you get. Then you give it a bucket full of this rock flour from Greenland, and your cornfield look like this instead. So we found out that in Ghana we could increase the yield of maize by 50% by putting this on the ground. That's really good. What we can also document is that every time we put a ton of this out in the field, we take 250 kilos of CO2 out of the atmosphere by this weathering reaction. So basically, we have in one package we have something that can take carbon dioxide out of the atmosphere by the millions of tons and can increase the food production on Earth for the growing world population. So here's just one example of how you can translate some simple geologic kind of background knowledge and a few observations into something that can have a global impact and can change the world to a better place. So I'd like to just do a more general comment in the end here. Here's a beautiful mountain. This is, again, doing field work in Greenland. You see, sometimes you have to go by a little 3-masted schooner for sail. That is not so bad either. But anyway, you see these mountains. This is about 1,000 meters high. This is 2,000 or 3,000 meters of deposition of material, and these are limestone carbonate rocks. All this is limestone carbonate rocks. You look at it and you think, okay, this is a mountain, that's fine. But what you look at is somebody's home. Oftentimes today we are very afraid of saying what we call leaving a footprint on Earth. Well, I would say we have to leave a footprint on Earth. Every organism that lives on Earth have changed the world, the whole world, the Earth. Every organism that have lived on Earth left a world that was different from the one it was born into. So our objective is not to not have a footprint, but to have a positive footprint relative to the way the world should work. So all these little carbonate rocks, they are actually little houses that organisms made to get a better environment around them than what is provided by the open ocean. And so all of this is intervention that somebody did for a purpose that we see here, and we think it's just a mountain sitting there. And every part of the world is one that is affected by some intervention that somebody did. So I think as humans, we should use our knowledge and our skill and our wisdom and our ethical and all these other compasses not to not affect the world, but try to affect the world in a way that is good for us and for everybody else on the planet. So I think that that should be my last words here for you. Don't be afraid of leaving a footprint, but be sure to leave a good one and make the world a better and a more beautiful place. And the world is going to be wonderful. Here's one of my fellow Inuit people from North Greenland, and this is what the world should be like. So thank you for your attention, and go out and do good things to the world.